Hi everybody, it's Mrs. Mancuso with some more AP Bio review. So I want to talk about data, and I want to talk about genetics problems and how you can look at the results of an experiment and figure out what happened. So let's say we were doing fruit flies. Crosses between fruit flies. Really common because you can have them reproduce in a very short amount of time, and you can look at traits really easy. So let's say that we do a cross, and we're crossing a fly that's wild eyes with a fly that has white eyes. And they give me these results. So here's wild and here's white. And let's say they went and separated and they told me how many males and how many females have these traits. And they say, all right, no males came out with red eyes, but 120 females came out with wild type red eyes. And then white, the males all came out with white eyes and the females didn't. So when they give you data like this and they separate the males and the females and you see a difference, you know right away this is sex linked. And so these males are XY and these females are XX. If the females all got this wild, they are getting the dominant trait. So they have to have a big A there. They are not, nobody ended up with this trait. So none of the males ended up getting the big A. Here are my males that I actually saw as a result. They're all X little AY. So if I think about the kids are X little AY and X big A, X something else. I now think about my parents. I know I had a wild parent and I know I had a white parent. The wild must be the dad. So dad gives his X to his daughters and gives the Y's to the sons. So this must have been a wild-eyed male. The white must have been the female because every single male offspring ends up with a little a. That means that every single XA that was given from mom had to be a little a. Otherwise, think about this. If instead this mom had been X big A, X little a, half of the boys, I wouldn't have 120 here. I would have had 60 and 60, but I didn't get that. So that's why I'm pretty confident this was mom, this was dad. All right, so I want you to be able to look at data and be able to figure out the parents from it and be able to figure out the type of inheritance. If you had a pedigree, here's mom, here's dad, and here's some kids. The daughter has the trait, nobody else in the family does. Can this be sex linked? If it was sex linked, it would be X little a, X little a. To get X little a from mom, that's a possibility because mom has two X's. One of them could be hidden, she could be a carrier. But here's where it's impossible. Dad does not have the trait. So this trait cannot be sex linked. A sex linked trait that is passed on to a daughter has to be seen in dad. Could this be a dominant trait? Nope. If this is a big A, where'd she get it from? To be a dominant trait, the parent, at least one of them, has to have the dominant trait. So that leads us to this is an autosomal recessive trait, little a. Both parents must be carriers. I know they have a big A because they don't have the trait. I know they have a little a because those two little A's are what give me this child. Over here, I'm not sure. This person might be big A, or big A, little a. When this son gets married, then I have a chance, maybe, of seeing which one it is. But if this is not a genetic condition that is of great concern, I might not ever know. It might not show up and it might not get passed on. All right, other inheritance problems. Okay, when you see data and it looks like this, I did a cross with a heterozygous and I did a test cross, which means I crossed it with a completely recessive. First of all, what would I expect First of all, let's put some traits to this so it makes sense. So let's say we're doing seeds, pea seeds, and big A is green, and little a is yellow, and big B is smooth, and little b is wrinkled. All right, these are the traits in my seeds. So I'm crossing a heterozygous green smooth pea with a homozygous or a true breeding yellow wrinkled. And I come up with each of the gamete possibilities for this parent. A gamete can only have one of each chromosome because it's haploid. So I have to put together A's and B's. I could put together a big A and a big B, a big A and a little b, a little a and a big B, and a little a and a little b. These are my 4 gamete choices. The way that you set up a Punnett square is you always come up with the possible gametes that could result. Only one A and only one B could be in each sperm or egg. Over here, there's only one possibility for sperm or egg. It has to have an A and it has to have a B, and there's only one choice of each. So instead of writing out the entire genotype, actually I'll do it. I might as well. There's my genotypes. And now I want to think about phenotype. How is it expressed? So this one would be green and smooth. This one would be green and wrinkled. This one would be yellow and smooth. This one would be yellow and wrinkled. So I'm expecting a 1 to 1 to 1 to 1 ratio. Let's say this is what I actually get. Green and smooth, I end up getting 472. Green and wrinkled, I end up getting 28. Yellow and smooth, I end up getting 34. And yellow and wrinkled, I end up getting 386. Okay, that is definitely not a 1 to 1 to 1 to 1 ratio. I am getting very, very few of these. These are what I call my recombinants. This one has both dominant traits, and this one has both recessive traits, just like the parent. So what is this telling me? This is telling me that the color and the wrinkleness is linked genes. And I can actually figure out the crossing over frequency. The chance of crossing over is what gives me these recombinants. So I'm going to add them together, 28 plus 34, and I'm going to put that over the whole. 472 plus 28 plus 34 plus 386, and then multiply by 100. I actually don't have a calculator right here. So let's say I do all this and I get 7. That 7% tells me that these 2 genes are 7 linkage map units apart on my chromosome. So again, I didn't actually do the math. You'd have to do the math to figure out this number. But I know because of this data that these genes are on the same chromosome. Here's the color gene. Here's the smooth versus wrinkled gene. On the same chromosome makes them carried together every time, which means that when you do a cross like this, you do not get your expected 1 to 1 to 1 to 1 ratio. All right, thanks for joining me for a little review, and watch some more.